Welcome to this explainer from Forge College. Now, have you ever actually looked at a Bitcoin address and thought, it just looks like a random keyboard smash? Or maybe like a Wi-Fi password that just went spectacularly wrong? Well, prepare to completely change your perspective on that today. We're going to reveal how these addresses are, in reality, highly detailed technical blueprints. They dictate exactly how unspent transaction outputs, our UTXOs, are locked up and secured on the blockchain. So we're going to decode these strings together. And by the end of this explainer, you'll be able to literally read an address and know precisely what kind of cryptographic lock it represents. Okay, so here's our blueprint for today. First, we'll look at the UTXO lockbox. Second, we dive into legacy addresses. Third, we've got the P2WSH complex lock. Fourth, we'll cover the SegWit upgrade. And finally, we're going to decode a blueprint in a real-world scenario. Let's get right into it.
Section 1. The UTXO lockbox. Securing the safe.
All right, think back to our last lesson on transaction inputs and outputs. You'll remember that every single UTXO is basically a securely locked safe, right? And it contains a specific amount of Bitcoin. But here's the thing, a safe is totally useless without a locking mechanism. An address is really just a highly specific human-friendly label printed right on the outside of that safe. It tells everyone exactly how it's secured. In technical terms, this internal locking mechanism is called the scriptPubKey. And to open that specific scriptPubKey lock, well, you need the right key, which we call the scriptSig, or in more modern terms, the witness. So when you text your friend a receiving address, you aren't just giving them a destination, you are literally handing them the exact schematic to build a custom lock for your Bitcoin.
Section 2. Legacy addresses. The P2WPKH padlock. So, you can actually spot these original legacy addresses out in the wild because they always start with the number 1. When a wallet sees this one, it generates a very specific locking script. You can see those OP commands laying out the exact rules there. But here is the hilarious catch. To actually open this legacy padlock, you have to cram your entire incredibly bulky cryptographic signature and public key directly into the main transaction data, right inside the scriptSig. I mean, it works perfectly fine, but it's kinda like trying to fit a grand piano through a dog door. It takes up unnecessary block space, and because of that, it gets unnecessarily expensive.
Section 3. P2WSH, the complex lock, the combination safe. Now, as Bitcoin grew, people naturally wanted fancier features, like multi-signature locks. But sharing a massive, highly complex lock with someone, that is a major headache. Enter P2WSH, or Pay to Script Hash, which solves this absolutely brilliantly. These addresses always start with a 3. Instead of building the whole complex lock right up front, a P2WSH address basically just says, hey, lock this with a hash of my secret rules. It completely hides the giant complicated logic, what we call the redeemScript, until the exact moment you go to open the safe. It's the ultimate bait and switch. It cleanly defers all that heavy lifting until you actually spend the Bitcoin.
But, yeah, there's always a but. Even with P2WSH, we still had a really chunky data problem. Jamming those bulky legacy keys into the transaction caused space issues. And worse, it actually allowed bad actors to subtly tweak the signature data before confirmation. That's a super pesky bug known as transaction malleability. So the million-dollar question for developers became, how do we shrink the keyhole to save space and boost security?
Section 4. SegWit, the modern upgrade, the side hatch safe. All right, enter SegWit. This stands for segregated witness, and it literally segregates the unlocking data. It's essentially like adding an express lane to the blockchain. Check this out. When you spend from a SegWit lock, your main keyhole, the scriptSig, is actually left totally empty. No way, right? Instead, your key and signature are passed through a completely separate data structure called the witness stack. By moving the key over to the side hatch, transactions become smaller, they get significantly cheaper, and they become completely immune to those signature malleability bugs we just talked about. It's a real game changer.
So how do you spot these high-tech side hatch safes? It's easy. They always start with BC1. Whether it's a standard key or a complex script version, whenever you see BC1, you are looking at this sleek, modern design. Actually, it is the absolute gold standard for efficiency on the network today. Section 5. Decoding the blueprint. Alice's transaction scenario.
Okay, let's put on our engineering hats for a second and see how this builds in practice. Step 1. Let's say our friend Alice wants some Bitcoin, so she hands you an address starting with BC1. Step 2. Your wallet software is super smart.
It instantly knows this is a native SegWit address and translates it into a very specific byte sequence. That's our witness program lock. Then, fast forward to step 3, when Alice eventually goes to spend that UTXO later on, the network will automatically demand that she provides her unlocking key strictly via that separate witness stack side hatch. So, that simple text address she gave you, it dictated the entire lifecycle of the lock.
And this right here brilliantly illustrates the complete master reference sheet. It maps out perfectly. The legacy padlock starts with a 1 and stuffs the key right into the scriptSig. The P2WSH combination safe starts with a 3, defers the complex rules but still uses that scriptSig. And then your modern SegWit starts with BC1 and cleanly slots the key right into the witness stack. You know, once you actually see the matrix here, it's a perfectly logical system.
All right, let's lock in our main takeaways. First, address formats strictly signal the lock type. They aren't just random letters, they are literal blueprints for the script. Second, your choice has distinct trade-offs. Picking a modern BC1 address over an old legacy 1 address is absolutely going to save you serious money on network fees. Finally, and honestly, this is a total lifesaver, all these formats have built-in checksums. If you accidentally make a typo when you're copying an address, your wallet is going to magically flag it as invalid, which saves you from accidentally locking your funds in a safe that literally no one on earth has the key for.
So I'll leave you with this final thought. Based on the exact address you are sending to today, what specific unlocking data will you need to build your next transaction input? Understanding this is the crucial bridge to mastering how transactions are actually formed on the blockchain. We'll be diving super deep into constructing those inputs in our next explainer, Transaction Structure Overview. Until then, continue your learning journey and explore more of our educational resources at forge.college. Thanks so much for joining me today, and I'll see you in the next one.